Good evening, sir.
हेलो हाँ जतिन सर आई आई ऑडिबल टू यू
Yes, sir, you are audible, sir. Yeah,
ओके मैं एक बार स्लाइड शेयर करके चेंज करके देख लेता हूँ वेदर
sure,
दे आर वर्किंग
sure.
या जस्ट तो अभी तक कैसा रहा प्रोग्राम
Sir, from the past 4 days, it's going on. तो अच्छा चल
ओके
रहा है सर. 150 प्लस पार्टिसिपेंट्स ज्वाइन हो रहे हैं एवरी डे.
ग्रेट
या और लास्ट में हम क्वेश्चन आंसर अभी तो सारे जो होंगे पार्टिसिपेंट दे आर इन द व्यूअर मोड ओनली.
ओके
तो उसके बाद फिर हम क्वेश्चन आंसर में उसके फिर उनके बाद से फिर हम ओपन करते हैं सर अभी.
ठीक है
ठीक है सर.
तो
सो
मेरी
सर.
स्लाइड विजिबल है क्या
Yeah, it's visible. Sir, okay, and okay, yeah, perfectly fine. Yeah,
या सो आई
done.
जस्ट वांट टू चेंज इट चेंज हो रही है
Yeah, it's working, sir. Perfectly fine.
ग्रेट
Yes, sir.
ठीक है सर ठीक है
So, I will send the mail to participants to joining the this event. है ना
श्योर
सर? तो
श्योर
तब तक so we will start at 6, 5, 6, 10.
श्योर
Okay, sir.
श्योर श्योर
Okay, okay. Thank you
ओके
so
सर
much, sir.
थैंक यू
Okay. Mm. Very good evening, all of you. Uh, I warmly welcome to all of you to our AICT Training and Learning Academy sponsored faculty development program on the title of Design, Development and Optimization of Electrical Vehicles for a Green Future, which was by AICT and which was organized by School of Electrical Engineering, Sri Mata Vaishno Devi University, Jammu and Kashmir. So I warmly welcome all of you. I also welcome our today's expert, uh, Dr. Krishna Kumar Gupta sir. So he is a assistant professor at the Thapar Institute of Engineering and Technology. He has a
Sorry, I'm sorry to interrupt you in between, Jatin sir, but Dr. K.K. Gupta is currently serving as associate professor in EIED.
okay. Okay. Okay, so sorry for that. So Dr. K. Gupta is serving as associate professor at Thapar Institute of Engineering Technology. He has a valuable expertise in powertronics and electrical vehicle technologies, and his insights on innovative converter architectures, efficiency improvements, and charging infrastructures will undoubtedly enrich eh, the the understanding of participants. So, on behalf of organizing team, our participants, I welcome to Dr. Gupta sir, and also to all the participants. And I request our student Anushka, please give the brief introduction on our today's expert.
Good evening, everyone. I am honored to introduce Dr. Krishna Kumar Gupta, an inspiring teacher, researcher, and author in the field of electrical engineering and power electronics. Dr. Krishna Kumar Gupta is currently serving as assistant professor at Thapar Institute of Engineering and Technology. As an associate professor. Dr. Gupta earned his BTech, MTech, and PhD degrees in electrical engineering from MANIT Bhopal. He has 7 years of teaching experience, having taught at institutions such as KIIT University Bhubaneswar and Sagar Institute of Science and Technology Bhopal. His research interests include multi-level inverter topologies, fault-tolerant converter, and renewable energy application. He has made significant contributions through numerous publications in top international journals, including IEEE Transaction on Power Electronics, IEEE Transactions on Industrial Electronics, and IET Power Electronics. He has also authored two academic books with Elsevier and holds an Indian patent on cascaded multi-level inverters. His excellence has been recognized with several honors, including Young Scientist Award by the MP Council of Science and Technology in 2015 and the CII Award for Excellence in Teaching in 2016 and his selection as a mentor of change by Niti Aayog for the Atal Innovation Mission in 2018. In addition to research and teaching, Dr. Gupta is a passionate mentor, having delivered expert talks and leading institutes such as NIT Bhopal, NIT Raipur, and NIT Jaipur. In summary, Dr. Gupta combines strong research expertise with passion for teaching and innovation, making impactful contributions to the field of power electronics and renewable energy systems. Please join me in welcoming Dr. Krishna Kumar Gupta.
Thank you so much, Anushka. K. Gupta sir, now I am handing over to you this expert session, sir.
A very good evening to all of you. Thank you, Anushka, and thank you, Akashdeep, and thank you, Jatin sir, for giving me this opportunity. Sir, can I share my screen now?
Yes, sir. Yes, just let me answer. Yeah.
Just give me a second. So, Jatin sir, is this
Yes, sir.
all these lectures, are they going on in the evening only, or like they have been going on throughout the
Yeah.
day?
No, it is only on 6 p.m. to 9 p.m., sir, for Tripura 5 days, 5 days, and
All right.
tomorrow it will start from 2 p.m., sir.
All right. So I'm sure all the
Exclusive.
participants must have been very tired now. So probably I'll try to keep this talk very simple and as much interesting as possible. And Jatin sir, can the participants ask questions in between?
Yeah, they can ask. They can
All right.
actually they can write the questions in the question answer box,
All right.
and at the end of a session, we will allow them to ask the questions.
All right. So I welcome all the participants. If they want to ask any questions in between, they are most welcome to do so. So this talk, like I have titled it as Advanced Power Converters for EV Charging Systems. And I'll briefly explain in a while, like why do we need to move to advanced power converters for such systems. And like this is a typical electric vehicle powertrain that you can see here. And uh, like our point of interest for this lecture are these two batteries. The first one is named as a high voltage battery, which literally may not be a high voltage battery, but we call it so because this is a traction battery. You're drawing power from this battery to run the motor, right? So this traction battery is typically known as the high voltage battery, because for all the other like DC power requirements within the vehicle, like you have another set of cells, another battery, which is called the low voltage battery. In terms of like commercial terminology, they call it uh, this battery. They do not call it a traction battery. They call it as an automotive battery. All right. So these two terminologies are used for batteries. So this high voltage battery is actually at the heart of whole of the traction system in electric vehicles. And much of the design of the vehicle as well as of the charging system is determined by this kind of battery. All right, so we'll take a look at the commercial landscape of electric vehicles in India and abroad. So these are specifications of some of the commercially available EVs in India. And here you can see that the voltage of the battery, it ranges from 72 volts to 356 volts. Some of the newcomers in the Indian electric market, they are using 400 volts also. This is like the landscape of commercially available electric vehicles, like popular EVs in the world. And our interest here is to have a look at the battery voltages for these cars. Again, you can see here that the voltages, they range from around 350 volts, 320 volts to 800 volts. In fact, some of the cars which are launched now, they offer a battery voltage of 900 volts also. The major reason, like to move from a low voltage architecture to a high voltage architecture, is in terms of the charging needs. You know, if you have a charging station which can deliver a current of 10 amperes, let us say, then for a battery pack of 400 volts, the power transferred to that battery pack will be equal to 400 volts multiplied with 10 amperes, right? So that will be 4 kilowatts. Whereas if you have a battery pack of 800 volts, then for the same current, the transferred power will be 800 into 10, which will be 8 kilowatts. So basically what you're doing is, if you increase the voltage of your battery pack, you are enhancing the overall power which is transferred to the battery, which is basically like fast charging of the system. So this is the reason like why we have moved from the low voltage architecture to a high voltage architecture. Of course, both these architectures have their own advantages and disadvantages. But for power electronics engineers, like this presents a huge challenge, because you need to design charging systems for 72 volt uh, battery pack for a car, as well as for an 800-volt battery pack for the car. So the industry standards are not yet fixed. So that is a huge challenge for all of us. Now, like typically, if you see the the relationship between the charging infrastructure and the power system. So I'm just explaining the typical ways in which we charge the battery. So what we call as the AC slow charging is actually uh, a way to charge the battery when you use the onboard charger. All right. So onboard, because this charger is installed within the car, so there is a limitation on the power, right? Which for the design for which you can, the power for which you can design this charger. And of course, you have the battery pack, and in between the battery pack and the charging system, you have what you call as the battery management system. So battery management system is a way in which the battery pack communicates to the outside world, and it has many other functions, like it acts as a data logger, it acts as a protection system for the cells, it enables the balancing of voltages amongst the cells, and it has many functions. So one of the functions is like to allow the charging or discharging of the battery pack. All right. So the AC fast charging is like when you use the onboard charger, but the power that you're drawing is from a three-phase system. So in India, like it is not a prevalent practice, but in Europe, they allow the installation of three-phase onboard chargers on the vehicles. So naturally, you can draw more power from a three-phase system, and the charging of the battery is faster. For further, like for better charging, faster charging of the battery, what we do is like we convert the AC available from the grid to DC with the help of what we call as an EVSE, electric vehicle. This is a supply equipment, and what we're doing here is like there is an off-board system where the charging unit is installed, and because it is an off-board system, it is outside the vehicle, so you have a lot of flexibility in utilizing the space. So we can design these charging systems with more power, right? So you must have heard about the charging systems which are proposed now by BYD for megawatts, in the range of megawatts. Of course, they may not be very practical because the impact of such chargers on the grid are not very desirable, but like that is what we are aspiring, that power range. So what happens here in this kind of charging, which is also known as DC fast charging, is that you convert this AC to DC, controllable DC, outside the vehicle, and then you forego the onboard charger. All right, you do not use the onboard charger. You bypass the onboard charger, and via the BMS you charge the battery. So what you're doing here is you are directly using the DC available at the end of the EVSC. So this is called DC fast charging. So before we move on to various like commercially available charging systems and the architecture, the requirements which are posed by a high voltage architecture, I'll just address some basics of power electronics which is employed in electric vehicles, for both for like traction system and charging system. So the simplest form of a power converter that we can understand like is a half bridge inverter, right? We call it as inverter because we have power available from DC sources, which are shown here as two batteries of voltage VDC each, and there is a load connected between these junctions A and B, which requires AC to function. All right. For charging systems, like we have this load, AC load is replaced with an AC source, and this DC source is replaced with a DC load. All right, but the principle remains the same. Of course, for charging systems, like the system is a bit more complicated because you have to synchronize it with the grid. But for our purpose, like this example will be sufficient. So the popular terminology is to have this rail is called positive DC rail, the higher potential rail, and the lower potential rail is known as the negative DC rail. So here we have used two switches which are marked as S1 and S2. These switches are typically like implemented uh, with a controllable part, which may be an IGBT or a MOSFET or a transistor, BJT, and like in anti-parallel there is a diode. So this part is called the transistor part, and this is the diode part. So this is basically to for bidirectional flow of current, but this kind of switch can block only one polarity of voltage. So we'll come to that later on. So this is a typically half bridge inverter. So what we are doing here is we are analyzing this structure, and this example shows us like how to analyze various other converters which are used not just for electric vehicles but for all kinds of applications. So what I have done here is like I have marked this junction B as my reference. So I assume that this potential is 0 volts. So if this potential is 0 volts, then this potential will be plus VDC volts, and this potential downwards will be minus VDC volts. All right. So what I'm doing here is I am turning on this switch S1 and I have turned off this switch S2. So when you turn on a switch, then ideally the potential difference between its two terminals is 0. So what happens is like at the higher uh, the the terminal which is at this point is uh, it has a potential of plus VDC. So the same potential appears at this junction A. So what we see here is that at junction A we have a potential VDC, and at junction B we have a potential 0 volts. So what we say is that the potential at A is higher than the potential at B, and the potential difference is the potential at A minus potential at B, which will be VDC. All right, so the output voltage, the voltage across the load here is this potential difference, which is VDC minus 0. Now, if I turn off this switch S1 and I turn on this switch S2, then what happens is like the potential minus VDC now appears across this terminal A. All right, so now the potential at B is 0 volts, which is what we have assumed. And with respect to this potential at B, the potential at A is minus VDC. So what we see is that the potential at A is lower than the potential at B. All right, so the potential difference is VA minus VB, so that is minus VDC. So now this becomes very interesting because for one combination, one switching combination, when S1 was on and S2 was off, you have a voltage across the load as plus VDC. And when S1 is turned off and S2 is turned on, the voltage across the load becomes minus VDC. So what you have done is that you have reversed the polarity of the voltage across the load. So when like these switching combinations for a power converters, they are called states, switching states. All right, so if you play around with these states, so for some time if you use the first state, then the voltage across the load is plus VDC, and for some time like if you use the second state, the voltage across the load is minus VDC. I have normalized it here with respect to VDC. So if you do it repeatedly, then what you get across the load is a square waveform. It is an alternating waveform because the polarity is reversing periodically. All right, so this simple example shows how do we use switches for converting one form of electric power to another form of electric power based on what kind of source we have and what kind of load is being fed by the source. So this process of manipulating the states, like here I used, for example, if I want an output voltage of 50 hertz frequency, then what I do is like for 10 milliseconds, I use first state, and for another 10 seconds, I use the second state. So for 10 milliseconds, I have plus VDC, and for 10 milliseconds, I have minus VDC, and I do it repeatedly. So what happens is that this is a periodic signal and the time period is 20 milliseconds. So I get an alternating waveform of 50 hertz here. So this process of like systematically altering the states of a converter is called modulation. All right. So these two terms are extremely important for us. One is the structure of your power converters, which is called a topology, and the way you are operating that structure, which is called its modulation. All right. So this is how actually we define power electronics. So what we are doing here is like we are dealing with the conversion and control of electric power. So in our example, what we saw a conversion where we are converting DC into AC, and we can control that because you have in your hand like the control of the frequency of that AC waveform. You also have in your control the magnitude of the AC waveform, but not for this kind of waveform, square wave. We'll see like for a PWM waveform, you have that kind of control. So in power electronics, what we are doing is like we are dealing with the conversion and control of electric power. Electric power comes in two forms, DC and AC. So all possible combinations we can do with the help of a power converter. Now, how are we going to achieve this kind of conversion and control? We are using semiconductor devices, and the speciality here is like these semiconductor devices, they are acting like switches, right? So they have multiple modes of operation, but we are using only their switching modes. The purpose of using them in their switching modes is that we get a very high efficiency because we know that whenever a switch is on, then ideally the potential difference across it is zero. So the power loss across that switch will be the product of potential difference and current. So whatever may be the amount of current, the voltage is zero, so the power loss will be zero. Similarly, if a switch is off, then the current through it is zero. So irrespective of the potential difference across it, the power, which is the product of voltage and current, will be zero. So practically also, like in when we use semiconductor devices as switches and we carry out this conversion and control of electric power using switches, the efficiency of such apparatus is very high. So you will find that for all kinds of power electronic converters, the size is very low as compared to the conventional converters which use semiconductor devices in their linear region. It's very less. The size is less because efficiency is high, which means that the power losses, the heat loss is less, and which means that the heat sink, the size of the heat sink, the cooling requirements, the fan, either natural cooling or forced cooling, those requirements are less. So this is a typical definition of power electronics, and we are going to analyze all kinds of converters using this definition. So I love to give this analogy to my students of a tap to differentiate the power electronics technology from the what we call as the linear electronics technology. Because whenever I ask my students like what do you mean by power electronics, mostly they answer it in terms of these two words, that when you're using electronics for high power, then it is power electronics. But this is not true. A power electronics converters may process a power as low as in milliwatts, and of course it can process a power of megawatts. So that is not always in terms of the amount of power that it is handling, but it is in terms of the way you are utilizing a semiconductor device. So this analogy of a switch is very important here, of a tap is very important here. So I have a tap here, and the water is flowing from this pipe, and we have a valve here which can control the flow of this water in the pipe, right? So if I open this tap, I operate this valve and I open this tap partially, then some amount of water is flowing through it, but it is not the full amount which can flow through this pipe, the full capacity. If I open it a bit more, then the amount of water increases, but still it is not the full amount. And I can I can have different number of different combinations where water is flowing through the pipe, but it is not up to the full capacity. And this is the condition where the the water which is flowing through the pipe is to its full capacity. All right. So all these states where the flow of water is partial, these states are called, these regions are called linear region, right? This region of operation for a semiconductor device is called the linear region. But these two distinct states where like the flow of water was completely zero here. So for a power electronic switch, the flow of current through the power terminals is zero, which means that the switch is in its off state. So that state is called the cutoff state or off state. And this state, when uh, the flow of water is maximum, it is fully saturated actually. This state is called the saturation state or the on state. All right. So when we say that we are operating a semiconductor device in switching modes, it means that we are operating it in these two modes. Any other operation will make it fall into the linear region of operation. And you must remember that, for example, we have all studied about BJT, that in its linear region, it acts like an amplifier. But in its cutoff and saturation regions, it acts like a switch. So when we say power electronics, it simply means that the device is being used like a switch. So for the example that we saw just now, we were trying to convert DC into AC. And when we talk about AC, like all of us electrical engineers, we know that, the what we call as the pure AC is a sinusoidal signal. It is a very smooth signal. It does not have discontinuities. And when we are trying to convert DC into AC, what we are desiring is this kind of waveform. But in our example, what we saw is that we got a square waveform. All right. So that was, the feature of that structure, the topology. Topology is an arrangement of, the sources, the switches, and the load. So that kind of connection is called a topology. And the modulation, the way you were operating the switches. So for that topology and for that kind of modulation, what you get across the load is a square waveform. So this is very distinct, although this is an alternating waveform, but this is not a sinusoidal waveform which was desired. All right, so it is something like this, this is, you recognize him, he's Amitabh Bachchan. And this is, some kind of imitation of this person where, you design your hair like this, you purchase, your specs to imitate him, and you grow a beard just like him. So this is something original, and this is an imitation of that. Now, this imitation can be very good and it can be very bad also. For example, you can have an imitation like this. You have long hair, you have some kind of specs, and you have some kind of beard, but you're trying to imitate him, but this imitation is very poor. In our example, the sinusoidal waveform is something that we desire. What we get is a square waveform, which is a poor imitation. So we want to move from this poor imitation to a better imitation. You cannot get a sinusoidal waveform directly from an inverter, because as I explained, like, you are using semiconductor devices as switches. A switch by nature is a discrete element. It is either on or off. So the waveform that you will get across the load will have that discontinuity in it. By contrast, the sinusoidal waveform is a continuous waveform. So by default, you are not going to get a sinusoidal waveform from that kind of switching operation. So when I cannot become Amitabh Bachchan, what I do is, like, I try to imitate him. All right. So this square waveform is a poor imitation of sinusoidal waveform. The better imitation of sinusoidal waveform is called PWM, which is pulse width modulation. So I'll explain, like, why do we need to move to pulse width modulation? What are the advantages and disadvantages of it? So I'll take example of I'll take help of a mathematical tool that we have all studied here. So I have this sinusoidal function of frequency f naught. I have another sinusoidal function which is the frequency of which is 3 f naught. So you see here is that like the time for which one cycle is completed for the first waveform. In the same time, the second waveform has completed 3 cycles. All right. So what I'm doing here is I'm adding a sinusoidal, pure sinusoidal function of 3 f naught frequency to a pure sinusoidal function of f naught frequency. So what happens now is very interesting. Like you get, as a result of adding these two waveforms, you get a waveform which is not sinusoidal in nature, but it is periodic in nature. All right, it is not sinusoidal as we can see it here, but it is periodic in nature. It will repeat itself, and its frequency will be equal to this frequency f naught, the lowest frequency component. All right. If to this waveform I further add another waveform of 5 f naught frequency, then what you see is that the original waveform has further changed. Again, it is non-sinusoidal, but it is periodic, and its frequency is f naught. So if I go on adding these, sinusoidal functions of, let's say, 7 f naught or 8 f naught, 9 f naught, like that, then what happens is like I get this kind of waveform, which you can see like it's approaching a square waveform. The kind of output that we got from our half bridge inverter. So what happened here is like I added a number of sinusoidal waveforms of different frequencies to obtain this square waveform. Let's call it square waveform. I can also say that if I break down this square waveform, then I get these sinusoidal functions. All right. This is called analysis. When you are breaking down a signal into a number of sinusoidal functions, that is called analysis. And this is because this is based on Fourier's theorem. This analysis is called Fourier analysis. So now we have reversed the logic. We have a periodic waveform. Fourier's theorem says that you can break this periodic waveform into a number of pure sinusoidal signals. The only thing is these signals will have different frequencies. So one component of this square waveform will have a frequency equal to this frequency, and all other components will be integral multiples, right? So we have a frequency of 2f naught, 3f naught, 4f naught, 5f naught, and so on. So this process is called Fourier analysis. It is extremely important for a power electronics engineer because to judge the quality of the traction inverter or the EV charging system or any of the power electronics equipment in general, we use this kind of analysis. So the terminology that we follow is that component of the square waveform which has same frequency as that of the original waveform, that component is called the fundamental component. All other components are known as harmonics. So if that component is of the frequency 3 times of the original frequency, we call it as the third harmonic. If it is 7 times the original frequency, we call it as the 7th harmonic. All right. So in our language, in the language of power electronics engineers, we say that whatever kind of waveform that we are facing, either for an inverter, for a traction inverter, or a photovoltaic inverter, or for an EV charging system where the desired input current is sinusoidal, we say that this component is not sinusoidal and it contains harmonics. In fact, in your practical life also, you have seen the effects of these harmonics. For example, at your home, if you have an inverter, you will observe that whenever the power goes off and your fan, if it's working on your inverter, then it starts making humming noise. The sound made by the fan changes and it increases. This is so because the output waveform that you're getting from your inverter has got harmonics, which are frequencies are higher than the frequency for which the core of that fan was designed, right? So that kind of difference you can feel when you shift from the grid power to the power which is provided by your inverter. All right. So these frequencies, these harmonics are extremely crucial parameter to judge the quality of an inverter or of any power converter, especially in the context of medical equipments that we use, right? So they are very much sensitive to the presence of harmonics. So this information that I have shown you here is typically represented in this form, which is called a harmonic spectrum. All right. So what I have shown here is a harmonic spectrum of a square waveform. It is very easy to read this kind of spectrum, because you see this is the order of the harmonic. All right. Zeroth order means 0 multiplied with the frequency of the original waveform, the waveform for which we are doing this analysis. So here we are doing this analysis for a square waveform. So 0 into F naught is 0, which means the DC component of that waveform. This is 1. So 1 into F naught, let us say if that waveform is of 50 hertz frequency, then this is the 50 hertz component. All right. And because this component has got the same frequency as that of the original waveform, this is called the fundamental component. So what we are doing here is, whatever is the magnitude of this component, we are calling it as 100. So this is a percentage, right? So this is our reference. This is 100%. Magnitude means the amplitude of that sinusoidal waveform, right? These are all pure sinusoidal components. So here the second component is not present. The third component is present, and its presence is very dominant, right? It is more than 30% of the fundamental component. So these presence of these harmonics in a waveform is described with the help of this kind of graph, which is called the harmonic spectrum. And I have actually taken it from MATLAB. It has got a tool called fast Fourier transform analysis, FFT analysis. So you can do this kind of analysis for any kind of waveform. All right. So this is important for us. We as power electronics engineers, what we imagine is that this original sinusoidal waveform is corrupted by the presence of these harmonics to give rise to this square waveform. This is how we talk about in power electronics about these waveforms. So that corruption brought about these harmonic components onto this sinusoidal function is quantified in terms of a quantity which is known as total harmonic distortion. Distortion caused by these harmonics on this sinusoidal function. All right. So what we do is we take the RMS values of all these harmonic components, we square them and we add them and we divide them by the square of the RMS of this component, fundamental component, and we take a square root of it. You must have seen the formula of THD. So for the square waveform, the total harmonic distortion, the distortion caused by these harmonics is around 48%. And what we see here is that the lower order harmonics are prominently present here. So in power electronics, we say that the lower order harmonics are difficult to filter out. We have to filter out these harmonics so that we can get a pure sinusoidal function, right? And that filter is implemented with the help of inductors and capacitors. These inductors and capacitors, they are acting like reactances, right? They are opposing the flow of these sinusoidal components. And for example, for inductor, we know that the reactance is equal to 2 pi f into L, right? So higher is the frequency, the more opposition will be offered by an inductor to the flow of sinusoidal current, right? So the kind of filter that we require here is a low pass filter, which should be able to pass this 50 hertz component, the fundamental component, and it should block these components. So it is difficult to filter out lower order harmonics because the amount of inductance required or the capacitance required will be very large. You will need large filters there. Okay. So this is a point that we have to remember, that the THD of a square waveform is 48% and it contains lower order harmonics. All right. So now this was a poor imitation of the original waveform, which was a sine waveform. Now we are moving on to a better imitation. Okay. So for that better imitation, we implement a scheme called pulse width modulation. So this is our reference. Like in that example, my reference is Amitabh Bachchan. So I take a waveform, the shape, which is what we require at the load terminal. All right. This waveform is a high frequency triangular waveform, which is called a carrier waveform. So what we do is like we compare at every instant of time, we compare the reference waveform with the carrier waveform, and this comparator gives you zeros and ones. Whenever the reference waveform is higher than the carrier waveform, it gives you a 1, otherwise it gives you a 0. So we feed those pulses to those switches of our converter, S1 and S2 switches. I'm showing it here, this kind of comparison. So this blue waveform is the reference waveform, the gray waveform is the carrier waveform. The frequency of the carrier waveform is higher than the frequency of this reference waveform. All right. So what I'm doing here is at every instant of time, I'm comparing the reference signal with the carrier signal. So for example, if you see this red dot here and this red dot here. So for this duration, the reference signal, the value of the reference signal is more than the carrier signal, right? So your comparator gives you 1 for this duration. For this duration, like your reference signal, the value of your reference signal is less than the carrier signal, and the comparator gives you a 0 here. So it gives you a train of pulses of different width, right? That's why we call it pulse width modulation. We are changing the width of the pulse. All right, and the complementary pulse is given to the switch S2. And if you see the output waveform, it looks like this. Again, I have normalized it with respect to VDC. So for a period of 20 milliseconds, you see that the switches turn off and turn off multiple numbers of times. In the previous example of square wave, one switch was on for 10 milliseconds and it was off for 10 milliseconds. But here, the switch turns on for some time and turns off for some time and again turns on for some. So when one power cycle, it turns on and turns off multiple number of times. Now this is a very interesting waveform. It follows the pattern of a sinusoidal function. Again, like it has got discontinuity here, but the sinusoidal function, it is in the positive half cycle, it is low and then it increases and it goes to a peak and then again it decreases. So here also the width increases. You see here the width increases and then it decreases, and in the negative part it increases and then decreases. So this is an imitation of a sine wave, and we can perform a Fourier analysis of this PWM waveform also. And if you perform the analysis of this kind of waveform, you get the harmonic spectrum like this. Now this harmonic spectrum is very interesting because the lower order harmonics are almost zero here. The harmonic present here is a higher order harmonic. All right, this is a 17th order harmonic, and it is easier to filter out this harmonic as compared to lower order harmonics because the inductance required to filter it out will be less. But very interestingly, the distortion caused by the higher order harmonics is too much here. If you compare it with the square wave, for the square waveform, the total harmonic distortion is 48.34%. Here it is 145%, almost 3 times more than the square wave. So here lies an important lesson for all the power electronics engineers. THD must not be the only criteria to judge the quality of a converter. All right, you can say that the THD of a square wave inverter is less, so it should be preferred over a PWM inverter. But this is not true because the square wave inverter has lower order harmonics in it, which means that you will have to put a very large filter with that inverter. A PWM inverter, on the other hand, the lower order harmonics are not there, so only higher order harmonics are there. So the filtering requirements will be very less here. All right. So as power electronics engineers or as a specialist in, if you want to function as a specialist in EV technology, especially in the domain of power electronics, we must understand that THD is not the only criteria to judge the quality of a waveform or an inverter. All right. So this is an important discussion for us. Now we move on to, a standard topology which is used in traction as well as in rectification circuits. So here, what we have done is, like, instead of one leg, we are using two legs here. And now we have four switches, and at the center point of these legs, like, we have connected the load. So this is called leg A and this is called leg B. And again, like, we can analyze this converter, we can take this as the reference and these two points as the positive DC rail and negative DC rail. Again, we can carry out an analysis, like turning on certain switches and turning off other switches. And what happens here is, like, we get multiple states now, valid states. In the previous example, like, we got two states, one for plus VDC and one for minus VDC. Here we are getting like four states, but two of them are redundant in nature. Like, the voltage across the load will be 0 if you turn on S1 and S3. And it will also be 0 if you turn on S2 and S4 simultaneously, all right? If you turn on S1 and S4, now very interesting thing happens here is that the voltage across the load is now 2 VDC. In our previous example, the voltage was only VDC. So this is a better utilization of what we call as the DC link voltage. Again, here the voltage is minus 2 VDC. And if you operate the converter using all these states, you apply like modulation, appropriate modulation. So you should focus on this green waveform here. Again, this green waveform is a PWM waveform. This is the waveform across the load. And very interestingly, like, it is a better imitation of a sine wave because this waveform stays for some time at 0 value also. All right, so we call this waveform as a 3-level waveform. It has got 3 levels: plus 2 VDC, 0, and minus 2 VDC. The waveform, like shown here in blue color, is a 2-level waveform. It has only 2 levels: plus VDC and minus VDC. So intuitively, like, we can feel that this is a better imitation of a sine wave than this kind of imitation. This is also a PWM waveform. So if we perform a harmonic analysis of this 3-level waveform, what we see that the THD has reduced here. Like, for PWM, it was 2-level PWM, it was 145%. Here it is 77%. And not just that, the lower order harmonics are absent here also. Only higher order harmonics are there. And we can, design a filter of very small size to filter out these higher order harmonics. All right. But more than that, something interesting happens at the load side also. That is called the dV by dt stress on the load. All right, like for an electric vehicle, the load is the traction motor. All right, so this voltage is fed to the stator winding of the motor. All right, so if you see the stator winding of the motor, like, it has conductors, and in between, like, there is an insulation. So basically that can be modeled like a capacitor. So all the current that we want to flow through that stator winding is only through the conductor. We don't want the current to flow through the insulation part, because if current flows through the insulation part, then, like, it will damage its insulating property, and over a period of time, like, there will be a lot of in the wear and tear on the insulation part, and a time will come when there will be a direct short circuit in the windings of the motor, the stator winding of the motor. The turns of that winding will be short circuited. All right, so that current is called leakage current, and that component can be modeled like a capacitor. And if you remember, like, the current flowing through a capacitor is I is equal to C dV by dt, the rate at which voltage is changing. So if you see, for a 2-level inverter, at a given instant of time, the voltage changes from +1 to -1. All right, so the magnitude of change is 2 units, and the time that it takes to change is almost 0. All right, so I can write dV by dt as the change in voltage which is 2 units here. I'm expressing it in per unit system, and delta t, where delta t is tending to 0. So this is the dV by dt stress on the load. Whereas if you observe this waveform, the 3-level waveform, then what you see is that the change in the voltage is from 1 unit to 0, and then from 0 to -1, and -1 to 0. So the amount of change is 1 unit only, right? So the dV by dt stress will be 1 by delta t. Here it was 2 by delta t. And the leakage current is dependent on this dV by dt. I is equal to C dV by dt. So the leakage current here, in the case of 2-level inverter, will be twice at that as that of the leakage current, which is imposed by 3-level inverter. All right. So this is the second advantage of, uh, trying for different kind of topology and different kind of modulation here. The first advantage is that you have got a better harmonic profile, which means that the filtering requirements will be less. The second advantage here is that the dV by dt stress will be less. All right. So now, if you have a capability to further increase the number of levels, for example, we started with this 2-level waveform, +1, -1. Then we moved on to 3-level waveform, +1, 0, and -1. Now let's say that we have a capacity to, synthesize this kind of waveform across the load. So we have 5 levels here: 0, 0.5, 1, -0.5, and -1. So visually, like, we can experience that this is a better imitation of a sinusoidal function. And the dV by dt stress on the load is further reduced because this step is of the magnitude of 0.5 only. So as compared to a 2-level inverter, this 5-level inverter is imposing, 1/4 of the dV by dt stress on the load, which means that the lifetime of the load, which happens to be a traction motor here in our case, will be more if you use this kind of inverter, right? So these are the two advantages that I talked about from these case studies. But like the inverters which can synthesize these kinds of waveforms are known as multi-level inverters. Multi-level inverters were invented somewhere in 1970s, all right, and now we are using such inverters for traction systems, for charging systems, for photovoltaic inverters, for statcoms, for transmission statcoms, for HVDC, for all kinds of power electronic like applications. We are using these kinds of inverters. So they were invented way back in 70s, but the primary reason was not just this dV by dt stress and better harmonic profile. Primary reason was something else. So we have to go back to this study. Now, if you have a look at this, Jatin sir, are you there?
Yes, sir. Yes,
Yes, sir, we are here.
How much time do
yeah.
we have, sir, for this session?
Up to
Sir, to be
7.
honest, it is very, very interesting session. So I think we can go for some more time. Actually, it is very
Okay,
interesting, sir.
I'll just take a few more minutes. All right.
Sure.
Yeah. So if you have a look at this state, so here S1 is on, so it is short circuited, like equivalent of that short circuiting. S3 is on, S2 is off, the current flowing through is 0. All right. But what is the potential difference across it? So if you look at this terminal, the potential is plus VDC. And at this terminal, the potential is minus VDC. So although it is off, but it is experiencing a voltage stress equal to this plus VDC minus VDC. All right. So the potential difference across this switch S2 is 2 VDC. Similarly, the potential difference across this off switch S4 is 2 VDC. All right. This structure is called a bridge structure. The DC link voltage here is 2 VDC. This is plus VDC, this is minus VDC. The overall voltage is 2 VDC. And the voltage rating of this switch has also minimally it has to be 2 VDC only, because the voltage stress across this switch is equal to this DC link voltage. All right, so if you analyze all the states, you will find that whenever a switch is off, then the voltage, the stress across this switch will be equal to 2 VDC only, this DC link voltage. So this brings us to an important design parameter of a converter. Whenever you analyze a converter, you should analyze it like this, on and off states, the combinations of switches. The voltage rating of a switch is decided by the highest voltage that it has to bear when it is off. All right, that is how you decide the voltage rating of a switch. The current rating of a switch is decided by the maximum current it has to conduct when it is turned on. So these are the two parameters on which you decide the ratings of a switch practically. So now this is like very challenging for us. For some electric car, this DC link voltage is 72 volts. For some electric car, this DC link voltage is 900 volts. All right, so accordingly you have to choose these switches. And the current rating is dependent on the load. So the highest current which flows through the switch is actually, you have to take a margin of safety for that also. So based on that, you decide the current rating, right? So for practical design, you go for voltage rating when the switch is off, the current rating whenever the switch is on, and the switching frequency, which is a feature of the modulation that I explained to you. So multi-level inverters were invented for this reason. Now I said that, like, if you can have a 5-level waveform, then it will be good for the load, all right, in terms of the harmonic profile and the dV by dt stress. But how to synthesize this kind of waveform? So the very first invention, the first patent was filed for this kind of structure. Now this is a very simple structure. It may look a bit daunting, but it is a simple structure. So I have this full bridge here. The DC link voltage is VDC, which means that each switch, the rating of each switch must be VDC. All right. I have another bridge here. The DC link voltage is again here VDC, which means that each switch must be rated at VDC. So what I do here is, like, I operate the first bridge with 3 levels. So I have not shown a PWM here for the sake of simplicity. So the first bridge is operated in 3-level format, and this output is VO1, and this is the waveform. So this peak value is VDC, all right, and this is minus VDC, and it has got 3 levels, VDC, 0, and minus VDC. Now the second bridge here, it is also operated in 3-level format. The voltage across the load voltage should be VO2, and this is a blue waveform. So again, this peak value is VDC, and this is minus VDC, and this is 0. All right. So what we do here is, we connect these two bridges in series. So this lower potential is connected to the higher potential of the second bridge, and this point A and this point B is now the load end. So what happens at the load is that it is fed with a voltage which is equal to sum of VO1 and VO2. So if you add this 3-level waveform with this 3-level waveform, what you get here is a 5-level waveform, right? This is 0, this is 0, so addition is 0. This is 0, but this is VDC, so addition is VDC. And here it is VDC, and here it is VDC, the addition is 2 VDC. So what is happening here is, to synthesize an alternating waveform which has a peak value of 2 VDC, I'm repeating it, to synthesize a waveform for which the peak value is 2 VDC, you have to use power switches which are rated only at VDC. So this is very interesting, because you can generate a very high voltage waveform by using low voltage switches, right? You do not have to, normally what we do is, like, for an 11 kilowatt, even for to run a 400 volt AC motor, you need a DC link voltage of 600 volts. All right, so each switch must be rated at 600 volts. But if you are using this kind of bridge structure, then what you can do is that you can use switches of only 300 volts rating. So you don't have to connect multiple MOSFETs or IGBTs in series. All right. So in our terminology, what we say is that the voltage stress across the switch is half of the operating voltage. Operating voltage means the peak value of the voltage generated by this inverter. So this is the reason for why like this kind of structure was invented. Of course, other benefits are also very important because the harmonic profile of this kind of waveform is like very much apt for a better lifetime of the traction motor. All right. So this structure is called a cascaded H bridge structure. Right. So these are H bridges. These are cascaded. So if you look at the profiles, the product profiles of all the companies, ABB, Siemens, and all, they are all. It was patented in 1970. So after 20 years, like it was patent free. So almost all the major manufacturers, the power electronic manufacturers, they are offering this kind of product, where they are using 5 level or 7 level or more than that also. Like for transmission statcom, they are using 401 levels of waveform. So 401 levels means the waveform is as good as a sine wave. All right. So this topology is called a cascaded H bridge topology. So it is a part of like one of the advanced architectures that we use for uh, power converters that we use for electric vehicles. All right. So now, like one question may come here is that the number of switches has increased. So basically, the cost will increase and the reliability will also increase. So I am not going into the details of something practical that people have demonstrated, but in 2014, like IEEE Society and Google, they threw a challenge called a little box challenge, where they offered uh, a prize of 10 lakh dollars, and what they wanted people to do is to reduce the size of an inverter by a factor of 10 or 20. All right. So this is called power density. So what they called for is to reduce the power density of an inverter to 50 watt per inch cube. So they gave their specifications, and like many people participated, and these are the 8 teams which qualified for their final rounds, and their structures were tested for around 6 months in NREL, which is National Renewable Energy Lab in the US. So this team, like many industries, also participated in this. This team from University of Illinois Urbana-Champaign. This team, what they did is, the power density that was challenged by this competition was 50 watt per inch cube, and you see all the teams actually surpassed that. But the highest power density was achieved by this team. They achieved a power density of 216 watt per inch cube. All right, so that was a very small inverter. And very interestingly, to achieve this kind of power density, they used a 7-level inverter. Now, my question is like, how is it possible that you are using more number of switches? Like you are not using 4 switches, which was being used in standard H bridge, right? You are using more number of switches, but the volume of your converter is less. So that was very interesting. This happens because the dV by dt stress plays an important role. The losses across the switches, the losses become very less, and the overall like heat sink becomes very small. So you are actually able to achieve much higher power density with a multi-level converter. All right. And costing is not a very big issue here now, because there are many switches which are coming with integrated gate driver units, and like practically it is possible. The only thing is that you should be smart enough to modulate this kind of structure properly. So this question should be laid to rest, that if you increase the number of switches, the reliability will be less, or the volume will be large, or the weight will be more. This is not going to happen. You should be smart enough to properly select a topology and modulate it properly. All right. So this was a bit about advanced power converters. So I'm going to skip some of this part, and I'll just there are some more like structures like this which can help you to obtain multi-level waveforms. But my intention here is to introduce a very popular structure which is called a T-type inverter. Many of the like industry leaders in R&D, like they are recommending this T-type of inverter in for traction applications. So this is a very simple structure. We saw this half bridge structure which uses two switches S1 and S2, and as a result, like the output was two-level output. So what they do is like they introduce another switch S3, and when you turn on switch S3, then there is a short circuit across A and B, which means that the load voltage is zero. So you get a three-level waveform. It is a very simple operation, all right? But when you analyze this kind of structure, I am presenting these waveforms like for your help. Like if you turn on S1 and turn on S2 and S3, right? This is one state, and you have turned on S2 and you have turned off S1 and S3. Something very interesting here happens. This B is our reference point. This is 0. The potential across A is plus VDC. All right. So for this switch S3, the polarity is such that this terminal, right-hand side terminal, is at higher potential, and left-hand side terminal is at lower potential. All right. For another state, when you turn on S2, what happens is like B is 0, A is minus VDC, which means that now this terminal B, which is the left-hand side terminal of this switch, is at higher potential with respect to this right-hand side terminal, which means that you cannot use a standard IGBT or MOSFET with a feedback diode, right? So this switch is known as a bidirectional blocking switch. It has to block voltage because it is off. It has to block the voltage. A diode cannot block voltage in both the directions, right? So this switch has to block both the voltages, both the polarities of voltages, right? So this type of switch which we are using now, for example, this upper point is at higher potential and lower point is at lower potential. Then this IGBT is not on because you're not giving it a gate pulse. This diode is also reverse biased, so this switch is off. But if the lower terminal is at higher potential and this upper point is at lower potential, then this IGBT is off because you're not giving it any pulse. But this diode will be turned on because this anode is at higher potential. So it will give rise to undesirable switching. So you cannot use this switch, which is called a bidirectional conducting but unidirectional blocking switch. You have to use this kind of switch, which is bidirectional conducting and bidirectional blocking. So it can block the voltages of both polarities. So when you study such structures, advanced structures for EV application, you will find these kinds of structures. So you should not get confused that why they are using two switches here. This is just to implement a bidirectional operation in terms of voltage. It can block the voltages of both polarities. All right. So this is a very popular structure now, both for rectification and traction. This is called a T-type inverter. In fact, they are trying for these new generation of locomotives also, they are trying to implement this structure for traction inverter for this 9,000 HP that WAG engines. All right. So just to conclude, like I'll just show the power topologies of some of the popular chargers, and what you see is that like all of them are using the bridges in some form. All right. So if you are interested to go to this industry, then you should start with the study of the bridges, their properties, and how they are implemented in various forms. So this is from Chevrolet. Like this is now a standard PFC structure where you have a diode rectifier at the front end. Then this is a boost converter, and so this is the AC to DC part. And to charge the battery, like you have to have a DC to DC part plus a galvanic isolation between the battery and the grid. All right. So this is again an H bridge. Here also it is an H bridge. This is an active H bridge because it has switches. This is a passive H bridge. It has only diodes. All right. So this is for Tesla model. This is again an onboard charger. As I said, in many countries they allow three-phase supply to the onboard charger also. So again, this is a three-phase bridge, and this is again an H bridge, like it converts this DC to high frequency AC, and this is a transformer, high frequency transformer used for galvanic isolation. And again, that high frequency AC is converted to DC by this, and it is charged like this. All right. So this is again a two-stage converter. Now this is a vehicle to grid charger. So again, here you have an active bridge. Now here, instead of a passive bridge, they have another active bridge. So at the two sides of this high frequency transformer, you have two active bridges. So this structure is called a dual active bridge. Again, this is a very popular uh, topology for EV charging systems, for microgrid applications, and it is very complicated in nature in terms of design of this high frequency transformer. But again, if you are a master of this topology, then your employability will be very good in power electronic systems. All right. So this is a fully bidirectional, which means that the power can flow from the AC to DC side, and it can also flow from DC to AC side. Renault uses a very interesting structure where, for this kind of conversion, you need inductors at various stages. So what they do is, like, they use the machine winding as inductor. All right. So this kind of charger is called an integrated charger. It is a very complicated charger, but the space requirements become very less because they use the winding of the motor, the traction motor, as inductors. Again, this is a dual inverter charger, but my intention here is to come to this 50 kilowatt fast charger. Again, I told you that power is important for us. That's why we are going for high voltage architectures, because for the same current, we can deliver more power uh, to the battery. All right. Now we come to the off-board charger. So now this is again a charger from ABB, which is a very high power 150 kilowatt charger. Now once again, you need galvanic isolation between the battery of the car and the grid. All right. But now, very interestingly, you see here is that the galvanic isolation is provided at the front end, where you use an isolation transformer. Now this is a low frequency transformer, which is all right for an off-board charger, because you do not have a lot of constraint for space. For on-board charger, because it has to be installed within the vehicle, you have a lot of constraint. All right. So for this kind of system, where you want galvanic isolation between the load, that is the battery, and the source, which is the grid, you use, for EVSC, you use an isolation transformer at the front end. The limitation is that this has to be a low frequency 50 hertz or 60 hertz transformer, as compared to the high frequency transformer, which is used in a dual active bridge. All right. So most of the structures that you see for various charging systems, they are very similar in nature. All right. So this is I was talking about the 800 volt architecture. So that 800 volt vehicle was introduced by Porsche for the first time. It was introduced by Porsche, and this is the fast charging system that they are implementing for it. So they are using a three-phase transformer here, which is a phase shifting transformer. And very interestingly, this rectifier that they are using here is a 3-level rectifier. This is called Vienna rectifier. All right. So this concept of multi-level inverters and rectifiers, they are now mainstreamed by many companies, especially those which are using high voltage architectures for their vehicles. All right. So again, like this is the same slide where I talked about various voltage ranges, and you will see very interesting times in electric vehicle technology, because people are coming up with very innovative ideas. We don't know what voltages we will be settling. Probably we'll go for 400 volt architecture or for 800 volt architecture, because to have the economic advantage of scaling, these things have to be standardized. All right. So yeah, this is all from my side. If you have any questions, you may please ask, if you're still left with some time.
Thanks a lot, sir, for this wonderful presentation, moving from the very basics of power electronics to the advanced converters that are being used in industries, automobile industries, or
Yeah, thank you for staying awake.
literally it was very interesting. And after Thapar, I think I am attending this lecture from you.
Yeah, my
It
pleasure.
was really good to. So if any participant is having any questions, we can ask. And
So tomorrow is going to be the last day of this program, right?
oh yes, sir.
Great.
Dear participants, if you have any questions, please you can write the questions in your question answer box, or you can also raise your hands here. So we will allow to ask you the questions. Yeah.
Okay, so Satyajit Sahu, you have any question?
No, sir. Actually, thank you very much for giving me this opportunity.
I'm extremely
Actually,
sorry if you actually felt like a fifth sem student. I'm
yes.
extremely
Actually,
sorry
when
for that.
the session started, actually, I was completely down into the how briefly how all the harmonics, first, third, fifth, seventh, how you are describing all this. I completely felt like I was a fifth semester student, lecture, listening to the power electronics lecture that we hear. So I was
I'm extremely
completely.
sorry, sir. Like I designed it this way, so I'm
No,
extremely
no, no,
sorry.
no, no. It was like going back in time 10 years, 15 years. So it was like really refreshing. Sir, really like the students need to understand these things to actually
Yes, yes,
implement this in the EV charging part.
yes, exactly,
Often
sir.
we go so deep into research that we forget our fundamentals.
Exactly,
Yeah.
exactly, sir.
Thank you very
Actually,
much.
I found this, whenever we talk to the industry, they are not very much interested to hire UG students because of this reason. Unless your fundamentals are extremely good, it's very difficult to design power electronic converter for any application whatsoever.
Yes, sir. Thank you very much, sir. Thank you.
Thank you, sir.
So okay, sir, I think that it because it was really, wonderful. We dived fundamentally into the core concepts of power electronics. So I think everyone is cleared about the concepts and topics. So really
Thank you.
thanks, sir, for
Yeah,
this
thank you
wonderful
so much.
presentation and lecture, sir.
Thank you for this opportunity, and I thank all the participants also. Thank you so much. Jatin sir, what do we do now? Can I leave the meeting now?
Yeah, yeah, sure, sir. Sir, we will start the next session within a couple of minutes.
All right.
So, yeah, yeah. Thank you
Thank
so
you.
much, sir.
Thank you so much. Thank you, Akash.
Thank you.
Yeah.
Thank you, sir.
Yeah, very good evening, all of you. So, thank you for attending this session patiently. Now, we will move forward to our next expert session. It's my pleasure to welcome Professor and Dr. Abu Chandrasekhar, who is a professor in National Institute of Technology, Delhi. He will deliver the lecture on hybrid electric vehicle evolution in the 21st century towards green and sustainable mobility. So he is a distinguished academician and researcher who was expertise in contribution in the field of electric and hybrid mobility are highly recognized. His insights into the evolution of hybrid vehicles and their role in achieving sustainable transportation will provide the provide the participants with great learning and inspiration. So I request our student Aswini, please give the brief introduction on our today's expert.
Thank you, sir. Am I audible?
Yeah, better you're audible. Yeah.
Good evening, everyone. It's my privilege to introduce our distinguished expert for this session on hybrid electric vehicle evolution in the 21st century towards green and sustainable mobility. We are honored to have with us Professor Dr. Obu Chandrasekhar, professor at the National Institute of Technology, Delhi, who brings with him more than 15 years of academic and research experience in power electronics, electric drives, and sustainable mobility. Dr. Sekhar's research interests include power electronic controls of electric drives, special machines, modulation and control of multi-level inverters, FACTS controllers, microgrids, and smart grids. His work reflects a strong focus on technologies that directly support the growth of hybrid and electric vehicles. One of his notable contributions is a SERB-funded project on design and development of a switched reluctance motor drive for plug-in hybrid electric vehicles with voltage boosting and onboard charging capabilities, a project of national importance with a sanctioned amount of nearly 57 lakhs. This project highlights his dedication to advancing efficient drive systems and integrating charging technologies into next generation hybrid vehicles. In addition, he has contributed to the development of direct torque control schemes for induction motor drives and the design of multi-level inverters, which play a crucial role in improving performance, efficiency, and energy utilization in EV systems. With his extensive academic background, funded research projects, and practical innovations, Dr. Sekhar has been playing an important role in shaping India's efforts towards clean and sustainable mobility. Please join me in welcoming Professor Dr. Obu Chandrasekhar. Sir.
Yeah, thank you so much, Aswini. Sir, thank you so much for accepting our invitation as to be the expert in this Atal FDP, sir. So thank you so much.
Thank
Yeah,
you.
yes, sir.
Thank you.
I'm handovering to you, sir. Right.
Yeah. Thank you for your opportunity and thank you for your introduction. So I hope my screen is visible to everyone. I am audible.
Yes, sir. You are perfectly audible. Yeah. This slide is visible, sir. Yeah, you can make it in a slideshow module, sir.
Yeah, I already.
Okay.
I hope 1 minute. 1 minute. Yeah. 1 minute.
Yeah, perfect.
Now it is in slide mode, all right?
Yeah, it's perfectly fine, sir. Thank you so much, sir.
So
Thank you.
can I proceed now?
Yeah, sir. You can proceed, sir.
Yeah. Thank you.
Yeah, thank you.
Uh, Good evening, all participants of this program today. And today, let's 1 hour I will speak about my research topic and what I am working on hybrid electric vehicle evolution in the 21st century. So I'm working towards green and sustainable mobility. It's not only uh, mm, now entire the world is looking about towards green and sustainable mobility. So this is one of the interesting topic, and the potential research is also those who are working on this particular area. So it is one of the emerging topic. So let's begin with this. Because I was also one of the member in Ministry of New Renewable Energy. So if you see this, the India's climate-related commitments, so as our Honorable Prime Minister of India, Narendra Modi ji, has already announced, India will reach its non-fossil energy capacity by to 500 gigawatt by 2030. This is our first target. So based on the climate related commitments, based on our resources, So the non-fossil capacity, energy capacity, 500 gigawatts by 2030. And also to meet 50% of its energy requirements, electricity only, from the renewables by 2030. So this is again another commitment has given by Honorable Prime Minister to reduce the total projected carbon emission by 1 million tons in between the year 2022 to 2030. And also by 2030, reduce the carbon intensity of its economy by less than 45%. It is with respect to like 2005 to on 2005 basis. So like 45% the carbon intensity may be less, coming less. And another thing is we need to achieve the target net zero by 2070. So these are the commitments. So why I'm insisting on this is, so nowadays, majority of the people they are looking about AI technologies, GNI technologies, Chat GPT, some like advanced topics like computer and A and ML, these topics. But now it is an electrical engineering student's responsibility and electrical engineering faculty responsibility. Those who are working on this particular area, we have to take these challenges given by the Minister, Honorable Prime Minister of India, and based on the energy India climate commitments. Now, all these statements, whatever the statements I mentioned here, so all these statements will make as a one research area. Like India will reach its non-fossil energy capacity by 500 gigawatts by 2030. This is 2030. We need to achieve 500 gigawatts. This is one of the target we are planning. We have to reach this non-fossil energy capacity by 500 gigawatt by 2030. So at the same time, to meet 50% of its energy requirement. So again, renewable energies. So this renewable energy. So now government is spending crores of money about this, and also towards the climate related issues. And you see, in order to progress these commitments and where we are standing now. So India, where in actions. So in order to review this, if you look into this particular slide, and this slide motivated, so India, where in actions. You see, India will be the lead global recovery in energy demand. So we are the third largest energy consumer in the world, and also fourth largest crude refineries we have, like and third largest crude oil consumer, and fourth largest LNG importers. So this is the scenario where we are with respect to sustainable and green, with respect to energy perspective, as already made by the commitments made by the Honorable Prime Minister, that is 2030. So with respect to energy, you can see here the share in the global energy consumption rises from 6% in 2018. Now it will be going to by 2050, 12%. So like 100% growth, it takes more than 30 years to come to the 6% to 12%, right? Global energy consumption rise from 6% to 12%. And also you see the oil and gas primary energy consumptions to double by 2050 in all scenarios. So like for financial year 2021, it is 5%, and for financial year 2050, it is 10%. At the same time, gas is also like it is 65% to 251. So these are the India primary energy where in actions where we are standing. And what about this? Coming to this, so India's energy emission target. So we have made a like long-term goal and like short-term goal, and the roadmap based on the climate-related commitments, the India climate-related commitments. So we consider the roadmap for so like 2030. So what I have mentioned in my first slide, 50%, 500 gigawatts of non-fossil capacity, and 50% of installed from non. These are the by 2030 whatever the commitments already given by the government. So we already discussed in the first slide. And you know, by 2047, So energy independence. So now we have to take this. This is one of the challenge for electrical engineering graduates and the people those who are working in this green and sustainable energy. So 2040 is the energy independence, and 2070 is the net zero target. We are going for towards net zero target now. Now the first target is 2030, and after that 2047 and 2070. So this is the roadmap. And in order to achieve this roadmap, so you can see the net zero targets given by the different countries in the world. So India has committed for net zero net zero target like 2070 we are planning. And USA, Jatin, some disturbance is coming. I think can you please control the disturbance. Thank you. And like USA, like 2050, USA has committed for net zero target 2050. All these countries are given like the span of 2045. You can see the Germany. So Germany is in advanced stage. So they are committed for 2045, and rest of the countries are most of the countries they are saying 2050. But now India has committed for 2070 at the net zero target. And in order to achieve these net zero targets, what we need to do, what we are expecting, and what type of things we need to do. So these things are now a burden budding electrical engineering students or maybe researchers. So this is one. So I will give a little bit of thought what I am doing to achieve these targets. And you also see the pledge from net zero emissions. So like different countries. So here, the pledge for net zero emission, it depends upon only three major factors. The first factor is 100% electrified sales, including battery, plug-in hybrid electric vehicles, fuel cells, hybrid EV technology. And the second factor is 100% zero emission vehicle sales. So this is thought second factor. It depends on only three factors, that is net zero emission. One is 100% electric sales. Another one is 100% zero emission vehicle sale, including battery plug-in and fuel cells. And net zero pledge the carbon neutrality and no more greenhouse gases emissions. So these are the three factors are considered, and based on these three factors, the different countries have given the commitments for net zero emission. You see, like 2025, the Norway has committed. Norway has been the sale out of IC engines by 2025. Already they committed. So IC engine based vehicles are not using by this Norway country. And if you see by 2030, like Denmark and other countries, Netherlands, Scotland, UK, they are also committed for like 100% electrified sales and net zero pledge. I have given the unmarked colors also. Like China and Japan also by 2035. If you see our country, we considered for net zero pledge is 2070. And these are the different roadmaps for different countries with respect to the three parameters what I mentioned: 100% electric fuel sale and 100% net zero emission vehicle sale and net zero pledge. So these are the three factors they considered, and this is the roadmap for different countries in the world. And now you see the world is moving towards the net zero, with many countries already set their targets. You can see like over 67% of the global GDP is now covered with the net zero targets. Most of the countries they are committed. Almost 67% of the global GDP is now covered with the net zero target. And more than 100 countries worldwide have committed for net zero carbon target by 2050. This is expected further increase. Maybe the conference is happening in 2026. Maybe it may be further increase. As of now, more than 100 countries they targeted. And 56% of the world top 250 companies already acknowledge the risk of the climate changes in the financial reporting. So this is already more than 50%, 250 companies are already acknowledge the risk. I think now you can see in Delhi. So now the temperature is almost now, maybe in Jammu also, maybe the temperature, I know earlier I was in Kashmir. So the temperatures, nighttime temperatures is maybe gone. But at the same time in Delhi now the pollution levels are also coming up. So because of the global, these factors now we need to consider and see more than USD 500 billion were globally invested to decarbonization effect by 2020. This is another point. More than 500 billions were globally invested for decarbonization effect. And limited global warming to 1.5 degrees centigrade requires the net zero CO2 emission by falling by 45% by 2030. You can see if you reduce the temperature by 1.5 degrees, the limited global warming. So maybe we are achieving this net zero target by 2050. So these are the towards the net zero, which many countries already set there. This is the target. More than 100 countries already they committed for net zero target, and 56% of the world and top 200 companies they already acknowledged the risk analysis and risk that they have analyzed. And this is a brief uh, about the climate related commitments. What world is looking. And now we will come to the our topic today. So in order to achieve this net zero target and 100% sales, electric sales. So now as an electrical engineering, so now we are now the what is history? Nowadays you can see most of the companies they are manufacturing these electric vehicles. So if you see about the history of this electric vehicle, it is not a new concept. It is started in 1837 and followed by 1884 and followed by 1890. So you can see how it has started from Scotland. Again, it comes to the different countries like UK and USA. USA has introduced in 1890 like 14 million, 14 meters, miles per hour electric vehicle with six-seater has already developed in 1890. It's not a new concept. It is already existing. And now we are taking this particular concept and we are using this. You also see, we know the major heart of this electric vehicle is like electric motor. So it is like a heart of the electric vehicle is an electric motor. So there are various types of electric motors that are used in electric vehicles. Like there, like if you take a DC series motor, a brushless DC motor, permanent magnetic synchronous motor, a three-phase AC induction motor, switch reluctance motor, and flux reversal motor, and linear induction motor. These are the electrical machines which are majorly used for to propel the electric vehicle application. So now you see the first DC series motor or maybe induction motor, three-phase induction motor, the first one and fourth one, we already committed and we are already delivering this particular course to our BTech and UG level as well as PG level students. Now the special courses like the special missions like brushless DC motor is nowadays it is also integral part of the course curriculum, the brushless DC motor and permanent magnetic synchronous motor. And now the other motors like SRM motor, there is some research going on this FRM, switch reluctance motor, sensorless control of switch reluctance motor, designing of SRM motors. And another motor is like flux reversal mission. What is this flux FRM? So today I would like to emphasize more about this FRM, flux reversal mission. What is the significance of this FRM motor, flux reversal mission? And also the linear induction motors, how it may be useful for the electric propulsion system. So I cannot give more about this DC series motor because it is already presented in our curriculum. So I don't want to discuss much about this. So these motors are mainly used for the railway application purpose only. Okay. You see this brushless DC motor. So maybe you see the construction. It is brushless. It is called the brushless because it doesn't have a commutator and brush arrangements. And also it is similar to a DC motor with permanent magnets. We consider as a permanent magnets here. There are two types of BLDC motors are available. The BLDC motors are suitable for high power density approach. Like if you take out the two types of BLDC motors, you can see outrun type BLDC motor and in-run type BLDC. What is this outrun type and what is in-run type? Where we are using this outrun and in-run type? How it will be the configuration? So most of the two-wheeler applications and also three-wheeler applications. Now earlier I think four-wheeler application also we're using this BLDC motor. So if you go further details about this BLDC motor, they classified like as a outrun type and in-run type. I'm not here to explain the operation of BLDC motor. I'm just insisting where exactly where we are using this in-run type and out-run type BLDC motors in present scenario of electric vehicle system. You take this out-run type BLDC motor. So you can see here outrun type BLDC motor. So this is what I'm saying in this type motors are. So the rotor of the motor is presented outside. You can see here. So this is the rotor and it is presented on the outside. And stator is inside, I think. The stator is presented on the inside. This is like as a hub motors. We call it as a hub motors, like plug and play motors here. This is very simple. Like two-wheeler applications, majority of the industries, they are using these two-wheeler applications, like hub motors only they are using. So this motor makes a overall vehicle less bulky and more compact. And also the requirement, there is no requirement of gear mechanism system. There is no need of gear mechanism. It is very simple. Uh, Bulky, less bulky because there is no gear mechanism system here. And it's also eliminate the space. If there is no gear mechanism system, definitely the space requirements will also be less. So that is one of the advantage of this one. So eliminates the space requirements for mounting the motor and all. And this motor may be widely preferred for the cycle applications, like two-wheeler applications, electric cycle manufacturing like Kulika. And these are the companies like Kulika and Troxon. These companies are for speed vehicles they are using. So it is also used for the two-wheeler applications. See, this is the outrun type BLDC motor, and the outer periphery is the rotor, and inside the stator like. So the major application of this type of outrun type BLDC motor is it can be used for two-wheeler application. There is no gear mechanism system here. And come to the in-run type BLDC motor, it is like complicated. It's not like as a outrun type, it's an in-run type BLDC motor. So here, what I can say, the rotor, so if you take as a rotor of the motor present inside, this is just reverse what we have discussed in the earlier outrun type. But in-run type, the rotor is presented inside and stator is presented on the outside, like a conventional motor here. So like this is the conventional motor construction. So what I may say here is the rotor is the inside and the stator is outside. Okay. And here, definitely, if the rotor is presented in the what I can say, inside of the, so definitely we need as a transmission system, gear mechanism system is required, the external transmission system to transfer the power to the wheels. So it's a little bulky compared to the outrun type configuration. So now this type of motor is mainly useful for the three-wheeler manufacturing. If you see the three-wheeler, now you can see e-rickshaws are coming. So these e-rickshaws are majorly used for this in-run type BLDC motors only. You can purchase this outrun type BLDC motors from even Amazon is also now, maybe eBay. The e-market it is available. eBay market is available. Like it is cost is less than 3,000 rupees. So maybe this in-run type BLDC motors are costly compared to the outrun type BLDC motors because of this. And also I mentioned here the weight of the BLDC motor and also like the configuration what we have, like 48 volts to 96 volts, and this is 10 kW motor. The dimensions of the length and also mean dimension of the frame also I mentioned here. The main drawback it is due to the permanent magnets because this is a costly because of the permanent magnets, and also like it may be going if you go thermal conditions, if you are going with the higher temperatures, then definitely it will loses the permanent magnet. So that's why the thermal conditions also we have to see. So you see like this in-run type BLDC motor, the application, these are the three-wheeler type applications like we are using like I consider if you see in Delhi, so most of the areas in Delhi, they are using like not in Delhi, all metropolitan cities they are using like e-rickshaws. Now they are already this diesel-based autos. Now they are stopped, and now we are going with these e-rickshaws. So here, why the major focus about introducing this particular slide here is the maximum brake distance. It is like 2 meters only, and the motor rating, the motor power is 1 kilowatt, and the dimension of the motor, or what type of dimension we require, and maximum speed of this particular vehicle is only 25 kilometers per hour. This is one of the startup. Now you can also start if you want to do some research, or maybe start some startup company like this manufacturing of e-rickshaws. This is also good. Now I think few cities they are introducing, but most of the cities they are not using this. This is also one of the startup. You also think in that direction. And also like the charger specifications also I mentioned. So like 48 volts smps charger we are using. So this is about the another one is, if you take the permanent magnetic synchronous motor, the PMF, permanent magnetic synchronous motor. So this motor is like as a BLDC motor. This is also like just like as a BLDC motor. So permanent magnets on the rotor here. So again here, the BLDC motor has a trapezoidal back EMF, but this permanent magnetic motor has a sinusoidal back EMF is used here. So if it is a sinusoidal back EMF, definitely the torque, the smoothness of the torque will be more smooth compared to the BLDC motor, because the BLDC motor has trapezoidal in the shape, so it has like the torque ripples will be compared to more. And you can see the most of the automotive manufacturers, like if you see the Tata Nexon, MG Motors, all these companies, BM i3, they are using this PMSM motor. This PMSM motor is more popular for EVs now. Whatever the majority of the EVs are using this permanent magnetic synchronous motors only. And maybe it depends upon the power rating and type of motor. Again, it has two types of motors, PMSM motors, like based on the permanent magnetic mounting. So that is surface mounted permanent magnetic synchronous motor. Another one is interior or buried permanent magnetic synchronous motor, PMSM. So what is this surface mounted? So you see here in the surface mounted PMSM motor. So this is the rotor here on the outer periphery. This is outer periphery, and in the outer periphery we are attaching the permanent magnets by using epoxy glue, and then we call it as a surface mounted permanent magnets. And the thing is, these are surface mounted permanent magnets are not rigid type. It can be used for only low ratings, low speed applications, not for high rating applications, high speed applications. Whereas this interior permanent magnetic synchronous motors, like you see, you take here, what we are doing is on the outer periphery, inner periphery, there is some slot type, and in that inner periphery, we are including these permanent magnets, and these are the like what I can say, this type of interior permanent magnetic motors are majority of this is interior permanent magnetic motors only. They are using for nowadays for four-wheeler application, as well as like heavy buses also, lorries also, trucks also. They are using this one only. And coming to this is the interior permanent magnetic synchronous motor structure, how the different material, different parts are existing. So this is the way. And now I am working on this particular flux reversal mission. What is this FRM? Why we want to work on this FRM? If you see this Tesla motor, so they are using like internal permanent magnetic synchronous motors. They are using synchronous reluctance motor. They are using, but they changed the little bit of from the conventional flux reversal motor. They changed the little bit the structure. They changed, so that's why the basically now these axial flux missions, another we call it as axial flux missions. So how to use these axial flux meters for the propulsion of electric vehicle, and why we want to go these flux reversal missions. Now the thing is, we are depending completely about these permanent magnets based on this PMSM motor as well as BLDC motor. It is completely permanent magnets. The rotor, if you see the rotor, it is completely permanent magnets only. I think in the permanent magnets also, rare earth magnetic materials and non-rare earth magnetic materials are there. So now, if you see again, there is a classification about rare and non-rare earth magnetic materials. So if you see that non-rare earth magnetic materials are more costlier. No, rare earth magnetic materials are more costlier. That is niobium, iron, boron, and samarium, cobalt. These are the rare earth magnetic materials, and these rare earth magnetic materials are not available in our country. So we are getting from the China and Australia. So that's why, like non-rare earth magnetic metals are like ferrites, alnico, and alcomax. So in order to replace these permanent magnets, or the use of these permanent magnets, so the dependency of these permanent magnets, now there is another motor we call it as a flux reversal motor. The operation of this flux reversal motor is very simple, although it is a like conventional motor only, but the operation we are changing a little bit, some special arrangements we are doing. So what benefits, or why we want to go for this FRM motor? We are already we have a doubly silented permanent magnets and switch reluctance motor and FRM motor. You can see the comparison of three double silent missions. These are all of the doubly silent missions. So the magnetomotive force versus the phase flux. So like you can see the first figure, that is a doubly silent permanent magnetic mission, like your BLDC motor or your permanent magnetic synchronous motor. It is giving like two quadrant operation of the flux as well as magnetomotive force. But FRM is giving only one quadrant operation. But whereas this flux reversal motor, it is giving as a bidirectional. You can say, I can say like bipolar magnetomotive force and phase flux variation with the rotor movement. So that is enabling all directions. In all directions, you will get as a torque in this case. So the control of this SRM motor is more complicated compared to this SRM motor and PMSM motor, but the torque capabilities and the energy capabilities will be good in this FRM motor. So that's why now this is one of the prominent area the researchers are working on this particular topic. So you see the principle of operation of FRM motor. You take here. So what I'm doing this FRM motor here is, this is the pole shoe here. So on the outer periphery of the pole shoe, there is one slot, I think. So we are making as a two slots on the pole shoe. On the two slots, we are putting as a permanent magnets. For example, I am considering this 2x3 FRM motor, like two poles and three rotor teeth. So these are the rotor teeth here. So this is rotor teeth here. I'm making this is rotor, and rotor teeth are like this, and this is the stator here. So on the pole shoe, this is the pole shoe here, and here I'm making as a magnets. If you take here north pole and it is south pole, so like this is 2x3 pole FRM motor, two stators and three rotor teeth. So I'm considering here like four cases, like I'm visualizing here case A, case 1, case 2, case 3, case 4. So case 1, like you can see the zero flux linkage position. So what I'm doing here is, in the case 1, the rotor teeth is exactly 50% in the north pole and 50% in the south pole. So that's why there is no net flux will be zero. So at this position, there is no magnetomotive force with respect to the rotor position. So that's why it is in this position. When it is moving from this position, from initial rotor position is like this, and now you can make as a 60 degrees rotation. So what will happen here is, this is the initial position of the rotor. Now if you make as a 60 degrees in anti-clockwise direction rotation, so then what will happen here is, your rotor teeth is completely assigned with one particular pole here. So like this position it is coming. So like then the maximum flux linkages is possible. So the positive maximum flux linkage position is possible at this condition. So then when the rotor is moving from initial position to 60 degrees in anti-clockwise direction, so then maximum flux linkages are getting here. And from this position B2, again we are making as a 60 degrees rotation in anti-clockwise direction. Now you can see after 60 degrees again, so 50% of the pole is reaches with the south pole, and 50% of the pole is also reaches to the north pole. So then the net flux will be zero here. It is coming to zero at position C. And if you again from this initial position, from this position C to position D, again 60 degrees rotation. So then again in the reverse direction, it is entire maybe south pole is assigned here. So then negative maximum fluxes will be coming here. So what I'm doing here is, the idea what we are doing here is, we are putting the permanent magnets instead of the rotor permanent magnet. If you take BLDC motor and permanent magnetic synchronous motor, the rotor is completely permanent magnets. But we are not putting in FRM motor, we are not using these permanent magnets on the rotor, and the stator only we are putting, that too not a complete structure. So we are cutting the pole shoe, and the pole shoe we are putting like one part north pole as well as south pole, and that makes as a permanent magnets makes as a flux reversal. So whenever it making some flux reversal, so that will be in the sinusoidal flux we are getting. So by this, because there are different types of structures, so I mentioned only 2 by 3 pole FRM motor. So you can see like various stator and rotor pole configuration for FRM and parameters. So I have done like I designed so many structures through ANSYS software, and also like we are now manufacturing. We are also started doing experimentation on the same motor. So you can see like 6 by 8, 6 by 14, 12 by 16, 12 by 10. So 12 by 28. So these are the different types of the meter mission. And if you make number of magnets, so the number of magnets may be more, but the consumption, the magnet size, maybe we're reducing here. Okay. So, and then the torque ratio and how much speed we are getting and gear ratio. These things I have mentioned here. And you see here, like 6 by 8 pole FRM motor, and also 8 by 12. 8 by 12 means 8 stator poles and 12 rotor teeths I am using. You can clearly you can clearly see here. So here on the pole shoe we are making as a permanent magnet. So these are the permanent magnets, and then this is the rotor. So the rotor is like is a lightweight rotor. So there is no weight of the rotor. The weight of the rotor is very lightweight. It's like the teeth. So if you see the weight of the FRM motor, weight of the FRM motor and weight of the PMSM motor and weight of the BLDC motor, if you compare these things, so then the weight of FRM motor will be less because the rotor weight will be, there is no winding on the rotor, it's only blades. It's only the teeth, I think. So this is another way. And now what I am, the main problem is whenever if the rotor is having there is no winding, definitely you can produce more torque. But another thing in this conventional, if you take special missions like SRM motor or FRM motor, we are mainly suffering with this cogging torque. So how to minimize this cogging torque? So there are different types, different techniques to minimize the cogging torque. So what we consider here, there are three main techniques we consider. One is rotor pole pairing, and another one is rotor pole champering and rotor skewing technique. So these are the conventional, and we also know about these techniques. Okay, I hope I am audible, right?
Yes, sir,
Yeah,
you are audible, sir.
yeah. Thank you. Rotor pole pairing, you can see what I am showing in the rotor pole pair is, you can see the dimension of each rotor teeth. So this rotor teeth dimension will be more and this rotor teeth will be less. So like this, there is no uniformity in the rotor poles. So it is like non-uniformity. And then this type of rotor structure will minimize the cogging torque. We have already done the simulation and we are now and then rotor champering. So what is this rotor champering means? So you can see here from rotor pole pairing, the edges of the rotor pole teeth is here sharp, I think. So now we make as some curved shape here. So then this is called as champering. So this will increase the DC bus utilization. It is improving the no load voltage. No load voltage is also good under this condition. So pole champering. And we know this pole skewing technique, we know the magnetic locking and also harmonic reduction is also possible with this rotor skewing technique. And cogging torque is also one of the major issue. So then cogging torque is also reduction is possible with this rotor pole skewing technique. So my idea, what I did in my lab, so initially we tested like 6 by 8 FRM motor, and then we found with the conventional rotor, like conventional rotor means like what there is There is no rotor pole pairing, rotor champering, and rotor skewing technique. Normal technique we introduced. So, and then after that, what we did is, so we combined all these techniques like pole pairing, champering, and skewing technique, and then the combined technique also we proposed, and then we did the simulation. So this is the modified design of FRM motor. And you can see these are the 6 by 8 FRM motor. So if you use this rotor pole skewing technique, the skewing angle we considered only 20 degrees skewing angle with respect to the shaft position. So 20 degrees skewing we considered. And this is the two-dimensional 2D view of the magnetic flux, like a 12 by 16 pole model. And also the current density, like 12 by 16. See, why I'm considering this 12 by 60, we implemented for 6 by 8 FRM motor as well as 12 by 16 configuration also we consider. That's why I'm showing here. And you see, my main focus is, so how the conventional FRM motor is affecting with respect to the flux linkages of each phase and induced voltage in each phase and torque, average torque in each phase, and cocking torque, peak to peak cocking torque in each phase when we are using as a conventional motor, conventional FRM motor. So when we are using as a pole pairing technique, how it is doing, when we are using as a skewing technique, and when we are clubbing all these three techniques. So pole pairing technique, champering technique, and skewing technique, how these parameters, I considered 4 parameters. One is the flux produced in the each phase of the windings, and the induced voltage for each phase, and torque, average torque, and cogging torque here. So you can see the comparison table, what I proposed here, what I mentioned here. So by using this rotor pole pairing technique, the flux in each per pole is like 0.4 Weber. And then rotor pole skewing technique, the flux is like 0.26 Weber. And the conventional without using conventional thing is that this one, and the modified technique. So if I'm using this modified technique, so the flux value is almost coming low value because I am introducing all three techniques, so that's why it is coming low. But obviously my target is how to reduce the cogging torque. So reducing the cogging torque, at the same time the average torque should also, I have to maintain some value, good value I have to maintain, not some value. The average torque per phase, average torque is also high average torque I have to maintain. So now the induced voltage, you can see the induced voltage of the conventional model, it is maintaining 112 volts, and this modified 110 volt. And then the cogging torque is almost, now we are reducing. The conventional motor is 1.7 Newton meter, but this is 0.7 Newton meter. So torque also we are maintaining on our more or less the same. So what we did simulation. When it comes to the reality figures will be different. Now we are working on the same reality figures. And this is one thing. And these are the induced EMF waveforms of 12 by 16 FRM motor. And also the flux linkage waveform and cogging torque waveforms I have presented here. And another thing, what I did is, and this is another case, because as I told you, rare earth magnetic materials and non-rare earth magnetic materials. So when we are using, again, because why I consider this rare earth magnetic material and non-rare earth magnetic material is because these rare earth magnetic materials are not available in India. So like I told, samarium cobalt, nidorium iron boron. So these are the rare earth magnetic materials. Those are not available now. So whatever the magnet you are putting on the pole shoe, again, I am doing some analysis. So how much torque is producing when I am using the rare earth magnetic materials? How much torque is producing when I am using as a non-rare earth magnetic material? So again, I did the same analysis. So this is NdFeB, so nidorium iron boron, and SRFE is the samarium cobalt. So these are the techniques what we consider here, and then the existing rare earth magnetic material and the non-rare earth magnetic material. So I have done the analysis like cogging torque and torque, ripple, power limitations, voltage regulation, and efficiency. And I have also done when normally another if you see some IEEE transaction papers, they are considering only 20 degrees of skewing angle and 30 degrees or 25 degrees skewing angle, the rotor skewing. But I considered here only 15 degrees of rotor skewing angle I considered. And then when it is 15 degrees of rotor skew thing, and also I told you that rotor pole pair techniques. So these two techniques I introduced here. One is rotor skewing technique, another one is rotor pole pairing technique we introduced. And at the same time, again, one is rare earth magnetic material, another one is ferrite. This SRFE is the ferrite. So rare earth magnetic material and non-rare earth magnetic material also I did here. So this is one type of analysis we did, and experimentation setup also we perform. And another thing is I have also compared with the large scale, because if you go for higher applications, the cost analysis and for electromagnetic performance and cost analysis of rare earth and non-rare earth magnetic materials for flux reversal mission I considered here, like 10K kilowatt power scale. So this rare earth magnetic materials is a ferrite I am considering here, and the design like a 3-phase 6x8 pole, 10 kW, 370 revolutions per minute, and this is what another cost analysis also I have done, and these are the specifications what I considered for design specifications of my FRM motor: the rotor diameter, rotor gap, rotor diameter gap, rotor yoke. All these parameters I have considered. So based on these specifications and parameters only, we are designing in the ANSYS model. Both 2D model as well as 3D model we completed of 2-3 models, like 6x8 and 12x16 motor. And now we are working on 10 by another model is 10x14 also we are working. So this is another issue. And coming to that, sir, why you are working? What is the significance? So whatever I am doing with this FRM motor, and again I have to come up with the existing motors like BLDC motor and permanent magnetic synchronous motor also we are doing. For example, if you take per phase analysis, or maybe if you take 10 kW motor of permanent magnetic synchronous motor and 10 kW of BLDC motor and 10K about FRM motor. So these parameters now we are checking. What type of characteristics we are looking is the noise level is one thing, and manufacturing cost another thing, and efficiency and user applications. At the end of the case, at the end of the implementation part, so we will see so how much noise it is giving. If you see the Tata Nexa, people are saying it is giving some noise. So why? Because this maybe noise is another factor here, and also mileage, how much distance it is going. So these things, manufacturing cost also again we have to see. So I consider here BLDC motor, permanent magnetic synchronous motor, and synchronous reluctance motor. So see here the permanent magnets. The consumption of these permanent magnets in the BLDC motor is high, and PMSM motor is also measure the cost is of the permanent magnets only. Another one is now another motor, that synchronous reluctance motor. The synchronous reluctance motor, there is no concept of permanent magnets either in the stator as well as rotor. So there is no permanent magnets on the rotor as well as stator. Only copper and steel only we are using. So the major cost is coming down here. So magnetic business is not there here. So another synchronous reluctance motor. So this is another one, synchronous reluctance motor. This Tesla is using internal permanent magnetic synchronous reluctance motor. So there is some issue, some little bit changes they are doing in the synchronous reluctance motor. I did little bit changes on the construction of the synchronous reluctance motor. Then I have done with FRM motor. You can see the noise level. This synchronous reluctance motor having highest noise level. This is another problem. Now we don't want to depend upon the rare earth and non-rare earth magnetic. If you want to go with synchronous reluctance motor, the noise level is the another point. It is giving highest noise level. Why this permanent magnet is now using? Because it is having low noise level. Because the induced EMF or back EMF produced in the permanent magnetic synchronous motor is the sinusoidal level. Whereas your BLDC motor is the trapezoidal, that is another parameter. So there I think noise level is also low noise level for this PMSM motor. And the manufacturing cost, see, obviously when you are going for something achieve for better values, automatically the cost is also another point of view. You can see the synchronous electrons motor, the noise level will be high, and the cost of this manufacturing cost is low because we are not using the permanent magnets here. At the same time, the efficiency of the synchronous electrons motor will be low, and the permanent magnetic PMS motor will be high. And applications, now this synchronous reluctance motor is in the developing stage only. So now we are working currently developing technology, an alternative to the PMSM motor, and counter increasing the use of magnets. So we don't want to use the magnets here. So this is the comparison of the major motors in EV. And I don't want to explain this linear induction motor because it is I will skip, because I have also done this magnetic levitation application of this linear induction motor. Just quickly I will go. This is the conventional induction motor, which is the cylindrical structure. So you take as a the geometrical neutral axis A and A dash. So now if you cut this motor and then put it in a linear fashion, then you will get like this. So this is the case. So here I can say, so the stator and also rotor here. The stator is the permanent one and stationary, and rotor is moving. So windings I can say, the phase A and phase B and phase C. The principle of this linear induction motor is very simple, like a conventional induction motor type only, but now we are putting in a linear fashion. There I think I can say the force will be there, and here the thrust will be existing here. This is the design of linear induction motor. I have considered doubles. I have considered only single-sided linear induction motor, not double-sided induction motor. So you can see. So this is the primary winding. So this is the primary in the sense my stator, and the secondary is like as a rotor. It is my aluminum body. It is moving here. So what I am doing is I have developed the lamination. So single-sided linear induction motor. So SLM. So in the single-sided linear induction motor, I have considered the thickness of each plate. This is one of the plate thickness, and the dimensions I have mentioned here. And these are the laminations what we have based on this calculation, and we have done the cutting of all the plates. We are using the test bench in our lab, and then based on the test bench, after finalizing this lamination thickness, and then we are cutting all these laminations, and then we are making as a bunch of the core. I think this is like as a core, I think. And then after that, the winding arrangements, and we are also calculating the winding arrangements. The primary setup we have done in our lab. So this is the primary setup. In the primary setup, what I have done is like two-pole machine I considered. Because you see the number of slots 12, and number of poles 2, number of faces also 3, and then number of slots per pole per face is 1. So I have done some calculation, pole pitch and slot angle, all these things. I think you know these are the fundamentals. And then we consider here, after giving excitation, we need to find out how much of thrust is going. So that's why I have, this is the winding arrangement, single layer winding also we designed, and primary setup, primary winding setup here. And then to observe the thrust, I have considered this is the rail, secondary rail, some aluminum body we design, and then that aluminum body we are keeping on the surface of the stator. So then it is moving with the excitation. Whenever we are giving excitation to this primary winding, so then it is moving like this. So the final setup will be like this. You can see. So on this surface we are putting as a one insulation sheet, like as a wood as a one insulation sheet, and then after that we are placing the rail, so it is moving. Okay, and then and then we did some analysis of static magnetic field distribution. So each phase how much with different current excitations, that like 2.5 amperes, 3 amperes, and 3.5 amperes. And at the same time, the flux density variations also we observed, and we plotted all these things. And the variation of the air gap flux density with R phase as well as Y phase and B phase, it is coming as in the sinusoidal fashion. And we also measured the flux by using Gauss meter, how much flux we are getting in each phase. So that flux measurement also we did. And the DC excitation, when we are giving as a DC excitation to the primary winding, each phase, I consider here for 3 cases. First case is 2.5 amperes with 208 amperes, and 3 only the current excitation I am changing. I told you 2.5 and 3 and 3.5 amperes and voltage variations. All these values we are plotting, and you can see this is the insulation I am using, wood as insulation, and this aluminum bar. So when we are giving excitation, so then it is measuring the thrust also. I measured some thrust, how much thrust we are getting for a given excitation. So those calculations also we did, and then we plotted with the thrust characteristics with respect to speed, and thrust characteristics. This is the plot we got with respect to linear thrust as well as input current, and secondary velocity with respect to input current also we calculated. And this is the final prototype what we considered in our lab. So this is the case, I think, and these are the design specifications we have done. And I told you the permanent magnets. This is also one of the interesting topic if you want to do on the research, the materials. So this will go little bit deviation, but uh, for fundamentals we need to study about this ceramic and alnico and samarium cobalt and samarium cobalt and neodymium iron boron. So these two are the rare earth magnetic materials. So these are not okay. And non-rare earth magnetic is ceramic, alnico, and in ferrites we are using. So why we need to what is the importance and why we need to discuss about these materials? And these permanent magnets will decide the cost of the motor. No, why I'm telling is if you are using this neodymium iron boron, so the cost of the permanent magnets, so then the cost of the your EV vehicle, electric vehicle motor will be high. Or if you are using samarium cobalt, so as a permanent magnet in our EV, so then the cost will be high. So this Tata Nexon and MG motors, they are using this samarium cobalt. So that's the reason why their noise level will also be less. The vehicle noise level will also be less in this case. Why it is, I can say the energy product, the energy density. So if you take as a ceramic material, low energy density, and also low cost and high corrosive force. Okay, the Curie point temperature. Another one is Curie point temperature. So when we are putting as a maximum load on the vehicle, if you are going as a maximum distance, so then definitely the winding will generate as a heat. So the permanent magnets will not lose its property. So the Curie point temperature of this samarium cobalt and neodymium iron boron is 755 degrees centigrade. It will withstand. But whereas that's why the rare earth magnetic materials, so we are using only rare earth magnetic materials in the permanent magnetic synchronous motor. So I have mentioned here, Alnico also it's a cost value. So some neodymium iron boron and the samarium cobalt. So highest energy product. It means BH curve. If you see the BH curve loop, the highest energy product, magnetic field intensity of this rare earth magnetic material will be low, a higher value, as well as Curie point temperature will also be high for these two materials. And I told you this is one another thing. So where these permanent magnetic, rare earth magnetic materials are available, and what is the significance of these magnetic permanent magnets with respect to the total parts of the motor? If you take like 53% is the magnets only costing. So like if you take this inventions in the motor technology and de-risk the supply chain, so the cost structure of the electric motor, like global magnetic production, like I mentioned here. So the China is having these rare earth magnetic materials. So they are having the rare earth magnetic materials. Now they are dominating in the field of electric vehicle, and also these rare earth magnetic materials they are getting, and we and also Australia they have one. So I mentioned here in the where we are using permanent magnets, low as well as high. So I mentioned in the color like this. You see here the cost structure of electric motor. If you see this interesting thing is the cost structure of the electric motor is like bearings is 1%, shaft is 2%, and stator iron and 9%, but this magnets is a 53%. So that's the key factor of this permanent magnets is this is only. Okay, and that's why what we are doing development of magnetless motor. So the development of magnetic less, this is another potential research topic is development of magnetless motor, like synchronous reluctance motor only. But if you use this synchronous reluctance motor, you are getting high noise level. So now another thing is how to minimize the noise level for synchronous reluctance motor without using the permanent magnets. So this is the an alternative. And another thing is reducing the dependency on the rare earth magnetic materials currently like BLDC motor and PMSM motors. Then why you are talking all these things? Because all these things will be leading to our net zero target. All these things will be leading to the India climate related commitments or world climate related commitments. So this is what the research is going on this particular area. And some advantages also I mentioned, motor control and responsibility of regulating drive, all these things. So major benefits of the motor control. So one part I'm working on this particular motor design part only, especially with magnets, without magnets, and moderate magnets. FRM motor is like we can say moderately we are using the permanent magnets, not like exclusive extensively like permanent magnet synchronous motor and BLDC motors like this. So today I would like to stop my presentation by this. Dr. Jatin, if there is any queries or anything, then we will. Hello.
Yeah, sir. Thank you so much, sir.
Uh,
Thank you for giving this wonderful presentation today.
uh,
Thank you so much, sir.
is there any
Uh,
queries? Then definitely
yeah,
I will take
yeah,
few queries from the
yeah,
participants.
yeah. So, participants, if you have any questions, please you can write in the questions box, or you can just raise your hand in the Google Meet, so we can allow you to ask the questions. Yeah, you can also write the questions in the WhatsApp group if possible. Okay, I just got one question, sir. How can synchronous motor designs be improved to enhance torque density without using permanent magnets?
Those specifications, permanent magnet or synchronous reluctance motor you are talking?
Is how can synchronous motor rotor design, can be improved to enhance torque density without using permanent magnets?
Because see, without using, like, we need to go with special rotor design concepts. As I
Yeah,
told you, like rotor pole pairing, rotor champering, rotor skewing technique. So only the thing is, uh, we need to go with some special, some design techniques of rotor design techniques only we have to concentrate. So then only the noise level, as well as without permanent magnets, these things will be coming.
yeah. And I hope the participant got his answer. And another, I just got the questions right now.
Hello, sir.
Under, yeah, Satyajit, yes, sir. Yes, you can
Yes, sir.
ask the
Please,
question.
please, please. I'll be
Yeah,
next. Okay.
Yeah, please,
okay, no
please
issue.
ask, no problem, please.
No problem. You can ask. Satyajit, how you can ask. No problem.
Actually, thank you very much for this presentation, sir. Sir, do you see any other motors coming into this EV industry? Like any future predictions of which kind of motors can be used apart from the motors you showed it, sir? Please.
The thing is, synchronous reluctance motor now everybody is working, because if you see permanent magnetic synchronous motor, they are saying that it is having like uh, cost, I think, rare earth magnetic material. So now to reduce the cost of this electric motor, and dependency, not a cost, it is a dependency of the rare earth magnetic materials. So now we are going with the synchronous reluctance motor. So most probably, and as per my research thing is, so now the best alternative is the synchronous reluctance motor. But if you go with the synchronous reluctance motor, there also we are getting some problem with the noise level. So m- what I am axial flux emissions is the best alternative for this EV propulsion, because I am working on this as axial missions. I think axial flux motors.
Sir, what about the let's just talking about the noise levels. I guess it can be a trade-off as noise levels and this cost, like noise levels can be a good trade-off for the cost that we are experiencing, sir. And one of the major issues that we also face during the EV mobility is that a lot of these motors that we use are soundless, and when you you are driving in a city or something like that, sometimes you are on your subconscious mind and you are driving your vehicle and suddenly an EV passes by, because it is soundless. So you sometimes like feel that there should be a sound in the motor, so that you can really like feel that one vehicle is coming towards you or something like that. So noise level can be a trade off with the cost, considering the cost, sir. Can it
Yeah,
be the
yeah.
case, sir?
Noise level is one of the exactly. You are right. Whatever you said is right. Noise level is one of the major prospect we have to work.
Okay, sir, thank you very much, sir.
Yeah.
Yeah, dear participants, if you have any questions, please you can
And
write
one
the
more
in the
thing, those who are one more thing I want to discuss. If
yes,
you are interested in the this special motor design, so you can come to maybe like doing a PhD or maybe like doing a MTech or something. You can directly come and discuss with me in NIT Delhi, or my mobile number is there in the website. You can contact, no problem.
yes, yes, sir.
Definitely.
Yeah, so participants, if you have any questions or if you want to join NIT Delhi, you can just drop a mail to Professor Obujana Segar sir. You can also message him on his WhatsApp number. So thank you so much, sir. So thank you for giving this wonderful presentation, and we express our heartfelt gratitude to Professor Upajanda Sekar for delivering such an informative and thoughtful providing talk. So thank you
Thank you.
so much, sir.
Thank you.
Thank you.
Thank you.
And
Thank you, Jatin. Thank you, all the participants, for giving this great opportunity to introduce myself. Thank you. Giving my
thank
knowledge
you
to
so
all.
much. Yeah,
Can
thank you
I
so much.
leave now? Thank you.
Yeah, yes, sir, you can. Now, the participants, thank you so much for listening patiently this expert session. So tomorrow will be our last day of our Atal FDB program. So tomorrow we will start from 2 p.m. tomorrow. So there will be three sessions tomorrow. So please be there. Please join 2 p.m. tomorrow. So thank you so much. Now, thank you so much. So we are concluding these sessions today. So thank you so much and good night. Thank you.